and Nina talking this session. After this, we're going to make a group photo, right? The group photo will be done just outside the auditorium. You cannot get lost. If you get lost, stay here and I'll come and pick you up and take you outside the auditorium.
I guess meet right in where the break happens, and then we'll go out and take a picture together.
Okay, I'm very happy to introduce today John Langford, my friend and colleague for many years. And he's going to talk Occam's race. No LLM. Amazing. Thank you very much. Okay, go ahead, John, and you're one of our students.
Yes,
right?
I was one of Avram's students. I was one of Avram's students who didn't really know what he wanted to do, so I actually had two advisors. But I certainly enjoyed working with Avram quite a bit. And over time, I guess I figured out things that seemed interesting. So I'm going to talk about maybe we need to have an Occam's razor principle for transformers, which is related to some work that I did when I was a student, but also some other things as well. So I thought I'd talk about three things. One of them is something old from when we were actually your student. Something new, as in just came out, and then something for the future, which is really where the question mark comes in. So something old is progressive validation. This is a paper back in the day with Adam and Avram, where we're thinking about how do you do sample complexity bounds with online learning processes where you're changing things over time. And I actually find it remarkably relevant today, which is why I'm bringing it up. So the way that progressive validation works is you start with maybe a naive model, and then you predict with it, and then you train with that, and then you use that very slightly trained model to predict the next thing, and then you test on that, and you keep doing this over and over again until you get to a full, you go through your entire data set, right? So you have a model which is being updated. You're always testing one ahead of where you're training. And then you're going to compute a progressive value, which is the average of your test errors.
Are you doing one pass or multiple?
Just one pass, just one pass. And then you can prove a theorem, and it says that the expected value is sort of the uniform of the qualities of all of these different models that you have. And then you can prove that this deviates like a test set error, not like a training error. So this is, I think, the key thing here, because most sample complexity bounds that we were playing around with back in the day would depend upon the size of the hypothesis space or something like that, and you tend to get overfitting and things like this. Okay, so if you go and you look at training of these modern transformers, what it looks like is you have a bunch of GPUs, and the model initially is very naive, so you're going to compute your loss on a bunch of sequences in parallel across all the GPUs, and then you're going to update your model, and then you're going to do that for the next set of chunks that comes into the GPU, and then you're going to update, and then you're going to do that for the next, and so forth, right? And so you end up doing this. Maybe you loop over data, and maybe that matters. But often you don't loop over data.
It seems very related like to online to batch. So it's like an online.
This is we're just the same thing. We're online native, basically. We're not worrying about doing batch things, but certainly I think that you do care about the in transformer, so there's a lot of tricks people play, like they have the learning rate, which kind of ramps down over time, things like that. But the point I'm trying to make here is that this process, when you don't loop over data, is exactly the progressive validation process. And that means that you can just apply things. And I think intuitively practitioners kind of know this. They know they should trust their training error much more than they would otherwise. but this is why you can trust it. And so you can actually, if your data set is like pre-shuffled or something like that, you can say that looking at your training error is as good as having a holdout validation set and evaluating that. All right, so that's kind of a neat trick, which we worked on way back in the day. So that was fun.
The size of this holdout is the size of the entire data set? Effective size?
Yeah, that's kind of a fun thing there. You're right. In terms of the deviations that you get, that's true. But the thing to watch for is it's sort of the validation for the uniform draw of the different models. And so if you don't want to include these ones at the beginning where it's very, very naive, you may want to just consider a suffix. But nevertheless, it is very efficient compared to having a separate holdout validation set. And perhaps this matters even more in the context of transformer training because A, you're doing sequences, which means that the individual losses of a sequence are not independent. And you're doing log loss, which is not well bounded necessarily. It's approximately bounded, but it's not as bounded as a lot of other things. It's not like 0-1 loss. And so the natural variation that you encounter may be a little bit larger than you might naively hope for if every individual token was independent and if you're just doing 0-1 loss. And so the ability to have a larger validation set is helpful in reducing the variance. Okay, so this is just something that we worked on back in the day, and I don't know, I'm bringing it up because it's your birthday. But now let's talk about something new. So people have been talking about world models recently, and we've been thinking about them as well. When people think about world models, they often think about a replication of sensory experience, right? So you have your observation, you take an action, you have your world model, which predicts your next set of observations. I'm not going to do that. I just want to get that out of the way. I'm going to do something which is an implicit world model. So here you have your observation, you have some way to digest it into some representation, which you can then apply an action to and then predict the next implicit world model.
Why do you call that box ENC?
Encode.
Oh.
Could the encoding be like in language model? It's larger than the what's can. So is it really compressed, or could it be much larger than what goes in?
Well, certainly what I'm going to be doing will be compression,
Okay.
typically. But
Something to think about.
yeah, certainly we're creating an implicit representation. So the representation I'm going to talk about is implicit and compact.
Okay.
Whether or not this is true for all possible applications of those things, not clear. Okay, so why do we want to do this? Well, maybe being able to simulate the world is an important thing. But I'm going to show you that it actually can help you train smarter models, which is a fun side effect. So basically, I'm going to say this box gets better, even though you don't use this box at inference time. You can also use this box and do more.
So you're saying your encoding algorithm changes over time?
We're certainly doing training, yeah. And through the training process, things are going to get better. So let me show you the approach that we're taking, give you a sense of things. So let's just think about next token prediction. So standard GPT style transformers. This observation would typically be, so typically your observations and your actions are the same thing, they're just offset by 1. So O2 would be the same as the A1 that you try to predict here. They're separated here, but don't worry about that. So you're trying to run up through the transformer stack and predict the next token. And then you do that in parallel across all of them, and you kind of learn how to predict the next token. So that's standard. So we can predict this next token, but we can also predict this next latent. Right? So at the top of the stack, before you predict the token, you have some embedding. Let's call that the latent. And then we're going to take our predicted token and our latent, and we're going to predict our next token. All right, so now.
Stochastic or deterministic, or it's easy or hard?
It
should they
is
think about
stochastic. It is standard matrix, which
so
unembeds.
it's not like an extra deep learning.
Yeah, this is just shallow here, from
Okay.
here to here. It's just a linear layer.
I see, okay.
Right? There's going to be some depth here, but it's not that much. This depth is about, we call it half a layer in transformer. Right, so, so now what are we doing? So we have, I was showing you a picture before, which has an observation being encoded into some sort of latent, and then taking an action and mapping it into another latent. Right? And of course, you could do this over and over again, because if you have a latent, you could use that to decode an action that you could then predict another latent with, and so forth. Right. Okay, so that's something you can do, which is an important thing, because you can do this and it doesn't really impact the efficiency of training these things. So that's nifty. Right, so let's just go back to world models for a minute. So I'm going to claim that we're actually learning a world model here. But let's just talk about what a world model means. So I would say that a world model is basically a belief state and a transition model on those belief states. Right? So a belief state here is all the information from the past which is relevant for which future action to take. So it's like a summary of the past. And this is where the compactness comes into play, right? Because we're going to be compressing things down to a latent. Yeah.
What is the goal? Is the goal to predict the distribution of the outcome of the sequence of action, or the sequence of states, or the sequence of relation, or something totally different?
Yeah, I'm going to be a little bit ambiguous about the goal, because it turns out this actually, this is like a 3 or 4 in one blow type thing, right? There's several different things that you accomplish by doing this. One thing, which is obvious if you think about it a moment, is we can do speculative execution, right? That's helpful, but you can do more. Okay, so we want to get a belief state and transition model. A belief state is, there's 2 ways to think about it. It's sort of like, what is a summary of the past, which has all the information you need for the purpose of predicting the future. So you can have kind of a past-based notion of a belief state, or you can have like a future-oriented version, like what is the information which is going to affect what you should do in the future. So I'm mostly focused on the future-oriented version of a belief state. So we want all the information from the past which is relevant for the future actions we're going to take. Yeah, so at the moment, let's just imagine that we're trying to predict all the future words. Okay, but you could do something which is more concise, perhaps, if there's only a subset of what you care of the future that you care about. Like maybe you're doing tool calling in a transformer, in which case maybe you only care about the words that choose which tool is going to be called, not about the words of the tool call themselves, right? So you can play games like that. And then, of course, we have a transition model, right? So we just, something which, given the belief state and the action, predicts the next belief state. Okay, so let's go back for a bit. Let's just make an observation here. So we're trying to learn a compact belief state here. This forward operator, we're going to have two forward operators, right? So we have this forward operator, and we have the standard sort of inference style forward operator where you go all the way up the stack. And this is, of course, going to be more powerful because it has much greater depth of computation available. This one's going to be much faster, right? So that's a basic trade-off that you're going to run into. Yeah?
You don't have the error of trying to predict from Z4 and A4 or 5.
But you can do that. We're not doing that at training time, but you can certainly do that. That's what people do routinely.
Okay. I see, okay.
Dana?
It's a bit schematic for me. Just to fix some ideas, can you say a kind of example that this would be applied to? Because I don't know what kind of subject matter you're working with.
Yeah, I'll give you some concrete examples, but you can also just imagine applying this to standard pre-training. So you shove in an enormous number of a wide variety of subject matter data and language, and things happen. Yeah?
Two questions. So the belief state, should I think of it as like a part of the parameter or part of the context? And second, what's the connection to RNN?
Belief state is essentially the activations. So you have all of these past tokens that are input, and the model is going to be trained to predict the next token as well as the next hidden state. And this Z is the set of activations before you shove it into the linear decoder, which is typical in a transformer. All right, so we're learning a world model. And now let's back up for a moment, because is a transformer a world model? People debate this, and we can answer this question, right? Just a normal next token prediction transformer. Is it a world model according to this definition? Anybody brave?
40%.
It is a world model according to the definition because all the key values are a belief state from which you can transition forward. Because there is the slow path. The slow path is essentially a transition model, right? So the difference is sort of like two different world models that we're comparing. One of them is the implicit one in the set of key values of the transformer, and the other one is this relatively explicit one in this fast decoding head. Okay, so that's, why do we want to have two world models? Okay, so it suggests that let's see, does this work? Oh, yes, okay. Compact is a key word here. So it is a compact world model. It's a small world model. A transformer's notion of a world model is like they keep appending KVs over and over and over again. So there's no incentive in the system for it to be compact. Here we have an incentive for it to be compact. We're trying to find a small representation with the property that it can let you project forward into the future. Okay, so I'm going to show you that this is in fact what happens. We're going to make a proof. The proof is that the claim of the theorem is that you actually learn a compact world model, and the proof is very simple. It's by induction. So the base case is when you're at the end of the sequence, in which case anything's a belief state, basically. Okay, and then we're going to back up. And so in the induction case, we're going to say, okay, let's suppose that the latent is a belief state for the actions after t plus 1, right? It's an induction. And then if we predict the next token, if we predict the next token, then the latent must be a belief state for the next action. If you predict the next latent, then we have to have, by induction, the belief state for all the future actions. So we can think about this backwards. If you're at the end of the sequence, you back up one. If you can predict the next latent, that predicts the last token, and you predict your current token. Okay, you have a belief state, you back up one more, just keep backing up, and you have everything, right? So this is, of course, assuming that you have all the representational power and data and compute that you need. But this is the semantics of the loss that you're optimizing. That's what I'm trying to say.
So it's a finite horizon.
Finite horizon to the end of the sequence.
Finite horizon, what's the average reward?
Yeah, finite to the end of your sequence.
Well, if the end of the sequence is stochastic, then you cannot go from the end for backwards. That's the remark.
Yeah, I guess we're not training that way.
You're doing finite horizon, which is great for me.
Yeah. Okay, so the latent is a belief state becomes a belief state for all the future actions. Then your inductive case is satisfied, and you can go on. Okay, so we have a theorem that we can learn a compact belief state, or this optimization drives for a compact belief state. And the question is, why is this an interesting thing to do? Right, and so I'm going to show you an observation, which I can't fully explain, but I feel like we need some theoretical insight. Okay, so we're going to start with a taxi data set. So we have a source and a goal, and then you have a sequence of steps which connects the source to the goal. And so if you train a transformer with this data set, you can prompt it with the source and the goal, and it will try to fill in a path. So that's great. But we're not going to actually test it that way. What we're going to do is we're going to test it by putting in a source, a goal, a partial path, and then a deviation. And then we're going to ask it to complete. Does it go to the goal or not? And if you do this with a normal transformer, next token predictor transformer, it turns out that it does succeed fairly often, but it fails about, it did not work out right. It fails 15% of the time. How did that happen? Interesting.
Part of the failure?
Wow.
It's even in letters of letters, so it's more.
It's supposed to say 15%, not 1D%. But it fails 15% of the time. Okay. So 1.5, 15% of the time, it does not succeed. You don't actually have to read it because you can actually look at the red, which is a representation of the errors.
Okay.
So any red goes into the failure.
Every red is a failure here, where there's a hallucination that kind of imagines that you can go somewhere that you can't.
A map with any red is considered a failure. So how are you measuring?
I think any red at all it's a very stringent thing. It'd be great to achieve that, but we're not going to achieve that. We're only going to merely reduce it substantially.
What is the 15% measuring?
The fraction of the times that you start with a source and a goal, and a partial path, and the deviation, and it manages to complete to reach the goal. Yeah?
Is this like a Q function?
Q function? No. We're not doing any Q learning. We're
No,
just,
not Q learning. But you're sort of taking the unbiased estimate of the Q function. You have a prefix, and then you deviate in one step, and then you continue with the same policy.
yeah. I think of it as so Kian Baffa at Harvard came up with this particular game. And the idea there is that you want to model how coherent the transformer's internal notion of a world model is, right? If it has a good world model, then like a normal taxi driver, they go down the wrong street. Okay, well, they take some turns and they get back to on path, right? But a transformer, I mean, maybe doesn't actually know how to do that. Maybe doesn't have a good internal representation for things. And this experiment is saying, oh yeah, there's actually a problem. It fails 15% of the time to get to the goal.
I got a question about the
Yeah?
experiment. This looks like Manhattan.
Yeah.
Okay, Did you just do the experiment on Manhattan, or have you done it on other cities?
Just Manhattan. Okay, so if you train with the next latent, it's actually, that's supposed to be 5. I guess D is 5. Yeah, so it's a 5% error rate. And you can see that, there's less red here than there. So we dropped the extrapolation error by a factor of 3 using a more compact world model. Right? Okay, so why is that? I really don't know what happened to the text there. It's kind of impressive. All right, so the way I think about this is back in the day, there was a way to predict where the planets would be in the sky. So they had this epicycle system where you had to kind of have circles and circles, and it was a little bit flawed, but you could actually add epicycles and epicycles to make it less flawed if you wanted to. You could predict fairly well where the planets would be in the sky. And then there was a series of people, Copernicus, Kepler, Newton, and so forth, that came up with a different theory, the heliocentric theory, for why the planets were and where they would be in the sky. Right, and so why was this theory preferred? Okay, so first of all, there's a good impact from this theory. It means that if you go to Mars, you don't have to change your theory, right? If you have a geocentric theory and you travel to Mars, then you need a new theory. But if you have the heliocentric theory, you travel to Mars, you can still use the same theory. So you get extrapolation, right? So that's what we want. We want to have the ability to extrapolate. So why was this preferred? Well, in some sense, this was a more direct way to get at the observations, but this was somehow easier to describe and simulate, and so it became the preferred way to do things.
Has anybody ever just asked, like, if you look at Newton's laws of gravity and you say, I'm going to represent those in terms of x bits, and then I represent these epicycles in terms of y bits, and then compares the number of bits, the bits will be much bigger for this. Just a simple-minded Occam's razor. Is that kind of what you're getting
Quite
at?
plausibly, yes, that is what I'm getting at. So the simple right answer seems to extrapolate better. This is a simple right answer, and it extrapolates better. And if you go and you study what happens inside of these transformers, they are, to some approximation, a well-fit pile of heuristics, which happens to give you the right answer. They're not a simple right answer. And so this idea of creating a compact world model is driving towards a simple right answer, which tends to make them work better. So this notion of an Occam's razor bound has actually been around for a long time. So I guess there was this early paper where people were talking about this. You can think about the description size of things and relate that very directly to the number of samples you need to learn. However, this is not a good description of what's happening here. This is not pack learning because it's talking about extrapolation. Right? So this is all about in-distribution learning. So you have samples which are drawn from a distribution, and you talk about the error rate under that distribution. That's not what's happening here. We're actively choosing samples which are not from distribution, and then we're observing that we get smaller error rates with this approach. I really don't know. Interesting.
When you're saying we are getting smaller error rate, you mean training with deviations brings you a better policy than training without?
No.
No. So
No.
what do you mean?
No. I mean, I train with no deviations
Right.
with next token
Yes?
and with next latent, which next latent is really next latent plus next token.
Yeah.
and then I prompt it in this manner which has deviations.
Okay.
So it's out of distribution, explicitly out of distribution, and my error rate is 1/3 as much.
So you get a more robust policy. This is how should I think about it?
Yes.
This is a good sign for what you're doing. Very good.
It seems kind of fun, yeah.
Yeah. Have you applied it to other experiments yet?
Yes.
Okay.
Yeah, right, so there's something for the future here, which is how do we think about Occam's razor with respect to extrapolation, with respect to out of distribution? And there's clearly limits here. Out of distribution can't mean the opposite of in distribution because that would never work, right? But what is the scope of this? I guess I'm not clear. So we're talking about compactness in activations. We've gone from all the key values in a layer to one set of set of activations. But people have also played around with compactness in parameters, and there are instances I know of where people actually see some gains from that. Another way to try to deal with this is what you're saying. You train with a whole bunch of extra deviations, right? So you can kind of cover the space, make everything in distribution. But that's obviously somewhat expensive at times. It also kind of means you have to anticipate what the deviations could be, which may be possible sometimes, but maybe it's a little challenging. It requires some imagination. Can we avoid the need to do this deviation training with the right approach? I guess I'm not entirely clear. I guess the more general question is, this ability to extrapolate is clearly desirable. It's great to have your error rates drop by a factor of 3, but how do you most efficiently achieve this? I don't feel like I have an answer to this. I have evidence that things are possible here, but I don't feel like I have a good answer yet. Yeah.
Isn't it the case that if you had the optimal policy, it would have an deviation? I think this should be clear. In some sense, you want to learn the optimal policy. I trust you. And I think, so the way that I'm compiling your talk in my brain is that, okay, John is really talking about the POM DP, the belief states, and the deviations are sort of a hint on the Q function, and the compact thing is sort of compacting the belief states, sort of that you can learn, not sure if the Q function or the policy, you're learning the policy, sort of.
We are learning a policy,
Right.
and we are learning to compact the belief state at the same time. How am I doing on time?
We started late. You have 6 more minutes.
Okay, very good. So there's other things which aren't nice. It turns out that if you train in this way, you can actually, your transformer will tend to look ahead into the future substantially more. So there's this canonical problem called 24. The idea is you have several numbers and you use simple arithmetic to reach a target number. So it's also kind of a goal-finding like problem. And it's kind of famous because on GPT-4, I think the accuracy was 4%. So if you take a data set with, D is a 5 apparently, with 500,000 examples, and you train a next token predictor, you get about a 1/3 accuracy. If you train with this next latent approach, just looking one ahead at training time, you improve your performance by 20%. So there's a huge jump, which is just from a very small look ahead that you achieve. You can do bigger look aheads, you can use alternate approaches, but next latent gives you a big jump from a very small look ahead, and nothing really does better.
So what do you mean here by next latent? C90, you're predicting the 8? In fact, so like in this sequence, what is the next? You see 90, the first token is 90.
So you see so it would be 90, and then you predict the times.
Okay.
And then given the 90 and the times, you predict the 8. And then given the 90 times and the 8, you predict the equal, and so forth.
And the goal is to reach 24.
Yes.
It wouldn't just do minus, whatever gets you to 24.
Well, you have a constrained set of numbers to work with.
Ah.
Right, so and that's given in your context.
Okay.
Right. And then the next latent prediction is not expressed in tokens. You're predicting the latent itself. Right? So you have the next token prediction and you have the next latent prediction. Right. Okay, you can do speculative decoding. We've kind of discussed this already. But in general, with transformers, you can, if you have a way to guess ahead, you can then just try them out in parallel. And so your speed up is, so crawling up the stack is the slow part. You can crawl up the stack 3 times in parallel, basically the same speed. And so if you can guess ahead, then you can check things out. Right? And so this gives you a very efficient way to guess ahead. Right, and then, yeah, happy birthday. Progressive validation still matters. Things we worked on a little over 20 years ago, I guess, still matter. It's good. The compact implicit world models are really nice. They greatly reduce your extrapolation errors. And I feel like we don't fully understand. We don't have like a good, I don't feel like I have, with the Occam's razor bound for pack learning, that one I know. This one, I don't feel like I have a good grasp on it in the same way. And I would love to have a better grasp on it. So thank you. Avram?
So I wonder, it feels a little bit, I wonder if it's a little bit like some of these issues with trying to improve on imitation learning. So in one of the issues with imitation learning is if you only see correct sequences, then the moment you sort of step off of a correct sequence, you're not sure what to do. And in some sense, next token predictor is a little like that. Because you're only seeing, real, actual tokens. Whereas I wonder if in these compact models, it's sort of forcing you to not exactly deviate, but you're not you're sort of getting a little bit off of the path somehow. I wonder if there's anything like that. Can this be viewed as some way of trying to get around some of the issues with imitation learning?
Yeah, so imitation learning is, I definitely think of the transformers as doing behavioral cloning, which is imitation learning. And so everything we're talking about here seems very relevant to imitation learning and trying to make imitation learning more robust.
More questions, John? Yeah.
So, what is the architecture of the feed-forward network, like the NHS that we called, or like how do you train on that?
It's the 2-layer neural network. The only thing which is a little tricky is you want to collapse the signal from the from the token choice without expanding the dimension that you're operating off of.
I've just told you.
And we use the glue cross technique.
There was one question, Dom, from the
So if you assume that there's some invariant dynamics operating, then maybe by forcing Occam's razor, you have a better chance of finding it.
Yeah.
So that would be my guess, is that it's not extrapolating in dynamic space.
There's actually an experiment I didn't show you, which is very fun. There's certain problem classes that transformers can't solve because they're not state tracking systems. And it turns out that you can bootstrap a solution with a state tracking system. So you can bootstrap an RNN off a transformer trained in this way. And that allows you to, this is kind of a complex thing, which is why I didn't explain it, but it allows you to somehow achieve state tracking efficiently, because you can do efficient transformer training, and then you have everything kind of set up to polish off with an RNN.
One more question? That was. Okay, thank John again. So next